right, good morning, everyone. We're going there this morning. I think my iPad's going to work today, but sometimes I think stuff's going to happen and it doesn't, and that's all right. So far, for the last couple lectures, we've been talking about flexural members, and it's mostly in the context of beams, and mostly, even then, we can divide it further into joists and girders. Our joists are fully laterally braced by the steel deck, so the compression flange doesn't actually want to sway sideways. The beam does not experience lateral torsional buckling. And if we have a stocky section, we can get the plastic moment resistance. If we have a slender section, like class 3, we can get the yield moment resistance. And we're not going to talk much more about class 4 sections for this course. The other day, we started talking about what can happen when beams are not laterally braced at the compression flange. And so if a beam is laterally unbraced along the full length, it can experience something called lateral torsional buckling. And this lateral torsional buckling is an elastic buckling mode. It's very similar to the older elastic buckling load, and that's going to reduce the moment resistance. And we looked at this curve where for short beams, if the unbraced segment length was really short, we get plastic moment. For intermediate beams, we get sort of an inelastic lateral torsional buckling, and for long unbraced segments, we get elastic lateral torsional buckling. I waved my hands a little bit about, and this is where things are gonna, what the hell is this now? Okay, so basically what we haven't talked about yet is this omega 2 value. Basically in the example and throughout the lecture last time, we basically said, well, that's 1. And in fact, if there was no omega 2 value here at all, that was the equation that basically gets derived for lateral torsional buckling when you don't consider any kind of moment gradient. And we talked a little bit about L, but really we just said, well, in an example at the end of last day, if L is the entire length of the beam, if the compression flange is unbraced for the entire length, we went with that. Today we're going to focus on when L is different than the beam length. And 90% of the time, L for this equation is different than L for the beam length. Okay, so the L you use to calculate the shear moment is not going to be the same as the L that you use to calculate the unbraced critical elastic bending moment mu. And we're also going to look at situations today when omega 2 is not 1. And almost all the time, omega 2 is going to be a little bit bigger than 1. We're going to see for the most part, practically speaking, it's conservative to just take omega 2 as equal to 1. And for most of the girders in your example buildings that you're doing your design project based on, you're basically going to end up using omega 2 as 1 anyway, and we'll talk about why that is. Okay, so basically today we're talking about unbraced segments and moment gradient and how the unbraced segment length and moment gradient can change our lateral torsional buckling calculations. Okay, so this is what we looked at the other day. We introduced the idea of having this equation for mu, the potential to develop the full plastic moment resistance, and then there is an empirical expression here. If there is an unbraced segment length that was long enough that we weren't getting the full plastic moment resistance, there's a region where we get inelastic lateral torsional buckling. And basically we're going to say, okay, whether or not we get elastic lateral torsional buckling, inelastic lateral torsional buckling, or the full cross-sectional strength depends on the unbraced segment length. And in the example the other day, the unbraced segment length was just equal to the length of the beam. We use this equation to calculate the critical elastic bending moment mu. And today we're going to focus a little bit more on omega 2 and L, specifically when omega 2 is not 1 and when L is not equal to the length of the beam. So basically after lecture this morning, you should be able to, I put this back in here again because I realized I waved hands a little bit about the difference between braced and unbraced beams. I'll give a little bit more discussion on what's a braced beam and what's an unbraced beam. You should be able to identify the critical unbraced segment in a steel girder. So lateral torsional buckling is really going to be important in the context of your design project for the girders. Okay? You're not going to do lateral torsional buckling calculations for the joists. I'll talk about why that is again in a minute. But basically, your girders are going to be broken up into several unbraced segments, and you should be able to identify which one is going to be critical in that girder. And finally, you should be able to calculate the moment gradient factor, omega 2, and identify, I guess, the unbraced segment length for the different sections of the girder that you're going to be working with. Okay? Are there any questions about why these three things are important to us before we get into the technical material for the morning? All right. So I brought this up a few times throughout the course. This is a typical floor plan. It's the floor plan for like floors 1 to 3 in the example building that we've been working with so far in this course. And we'll recall some of the terminology here. The blue ones here are joists. They're the members that support the floor. The floor is nailed or welded down. The steel deck is nailed or welded down to the top flange of the joist. And so that connection to the steel deck is going to prevent that compression flange from swaying sideways. And so our joists, we're usually just going to consider as fully laterally braced. Okay, so joists in this class we'll consider as fully laterally braced and in practice as well. And then the red elements here are all the girders, right? And we'll recall that the girders support the joists, and so the joists apply load to the girder everywhere the joists frame into the girder. Usually it's as a series of point loads. And in addition to loading the girders, the joists are also going to provide some lateral restraint to that top flange of the girder. But otherwise, in between the connection of the girder to the column and the connection of the girder to the joists, basically each of these segments between the joists is going to be unbraced against lateral torsional buckling. And so the girders have potential to develop lateral torsional buckling in between the joists, and the joists both load and brace the compression flange at intermediate points. If we were to look at how this might change, in red here I've shown what the bending moment diagram might look like for the joists loading this girder in this particular case, right? So we'd have 1, 2, 3 point loads on that girder. And the fact that the joists are also there and they're connected to the steel deck, they're going to provide lateral restraint at those arrows there. So the black arrows that I'm showing are restraint against lateral movement of that compression flange. And basically what this is going to do is it's going to force any lateral torsional buckling that develops in this girder to happen in between these points of lateral bracing. Okay, so length for the brace, or for the girder here, if we were to consider the length of the girder, we'd be saying, okay, this is LG, the length of the girder. But when we're doing lateral torsional buckling calculations for one of these particular segments, this is the length that we're going to be using to do our MU calculations. Okay, so we're not using the length of the girder, we're using the length of the unbraced segment. And so basically we're going to treat each of these individual segments between the joists as almost its own beam. Every segment is going to have its own critical elastic moment to consider, and we're going to see today that the most critical segments tend to be the ones towards the middle of the girder. All right, so basically, as I was discussing before, both the load and the stability come from the joists. And if we were to take this girder here and model it as a simple beam with a pin and roller, oftentimes what I'm going to show here is, of course, the point loads from the joists. And every time there's a little X shown here, that's a point of lateral restraint. Not always will there be a point of lateral restraint where we have a point load coming in. That's only the case if the point load comes from a structural member that's also bracing the load. I'll talk a little bit today about when we might have a source of load that's a point load along the length of the beam that does not come along with any lateral support as well. Okay. Does anybody have any questions about any of these concepts before we continue on? Okay, so I had a pull everywhere thing, and I tried for like half an hour today to get it to work, and it's just not going to, so I'm going to, well, maybe I'll spray and pray here a little bit, hope it's going to work. No, it's not going to. That's okay. So as we talked about a little bit the other day, section 13.6 of CSAS 16 tells us how to calculate the moment resistance of an unbraced beam. And so we looked at this in an example the other day where we had a beam that was fully unbraced along the entire length of the girder. Today we're going to look at when the lengths might not be the same, and we're also going to look at how the moment gradient, which is basically the shape of the bending moment diagram, changes the lateral torsional buckling resistance of our steel beams. Okay, so omega 2, there are actually two equations for omega 2. And the first one we have here is for very simple situations, and it's going to pretty much be the equation you should use all the time for your girders. I'll show you a couple situations when you don't use this equation, but this equation is for linear moment gradients, which means the shape of the bending moment diagram is a linear function. It's not curved, or it could be curved, but it's essentially linear. Okay, so basically we already saw for girders that the moment diagram is a series of linear lines. And so for each of those unbraced segments, the moment diagram is basically going to be linear. And we're going to use this equation that's based on this parameter called kappa. I don't know why it's capital K here, but little kappa. And the way it's described in S16 is it's the ratio of the smallest moment to the largest moment at the ends of the segment. And if we have a beam that's bending in single curvature, which basically means the moments are basically in equal and opposite directions, something like this, right? That's going to bend your beam like this, and that's single curvature. Kappa is going to be a negative value. Whereas if we had a beam that had moments something like this, that would be double curvature, and in that case we would take kappa as a positive value. Okay, I'm not indicating that these are positive or negative moments on the beam. These are just the signs that we would give to kappa when we're calculating omega 2 using this equation. So how does this work? Well, basically we just calculate kappa as m1. M1 is the smaller of the moments on the segment. All of our girders are going to be in single curvature. They're simple beams. They bend downward. They're not developing any kind of double curvature based on the loading. And so all of our girders are going to have a bunch of segments. They're going to have a smaller moment and a larger moment. And kappa is calculated as the smaller moment divided by the larger moment. And because it's in single curvature, we assign a negative value to kappa here. Okay? So the first thing we should investigate with an equation like this, I guess first of all, this is sort of a, I don't want to say it's an empirical equation, but it's also not necessarily a theoretical equation. But what we should do is make sure that this makes sense for at least one situation. What do you think we should get as a value of omega 2 for the situation where m1 is equal to m2 and kappa is equal to minus 1? What should omega 2 be if m1 and m2 are equal? We talked about this very briefly last lecture. What should it be? Should it be 0? Should it be 2? Should it be 1? Well, if we recall that the derivation of the critical elastic bending moment mu was for a constant moment, which basically means a situation where the moment diagram is constant. That would mean that m1 and m2 are equal. Then omega 2 should be equal to 1, because omega 2 is only introduced to increase the moment a little bit to account for moment gradient. And so if m1 is equal to m2, then omega 2 should be equal to 1. If m1 is equal to m2, then kappa is minus 1. And what does this equation then give us for omega 2 if kappa is equal to minus 1? Can anyone do that quick mental math? Well, basically we get 1.75, and then we get minus 1.05 because kappa is minus 1, and then minus 1 squared is 1, so we get plus 0.3. 1.75 minus 1.05 is 0.7, plus 0.3 is equal to 1. So that gives us a value of omega 2 is equal to 1.0, which is great. What about other values of kappa? If kappa was 0.5, or basically if m1 is less than m2, is omega 2 going to start to get bigger or smaller compared to the case of m1 is equal to m2? What about m1 is equal to 0? If we had a 0 moment at the left-hand side and a moment of m2 or whatever it is at the right-hand side, kappa is going to be 0 in that case. Can anyone do that mental math for omega 2 if kappa is 0? What do we get for a value of omega 2 if kappa is 0? 1.75, right? We get 1.75 plus 0, and so basically as the moment at one end of the segment decreases, kappa gets smaller and omega 2 goes up. Okay, so as m1 decreases, omega 2 increases. And what does that tell us about the moment that would cause lateral torsional buckling as M1 gets smaller. As omega 2 goes up, what happens to our unbraced critical elastic bending moment? Well, if we go to the equation, it's proportional to omega 2, right? So as the moment diagram goes from constant to a linear value where the moment at one hand is smaller than the moment at the other side, omega 2 gets bigger, and that increases our critical elastic buckling resistance, okay, and increases our resistance in elastic lateral torsional buckling. So that's kind of interesting, and basically what's going on here is if the bending moment diagram is uniform, then the compression in the flange for a uniform bending moment is going to be the same. It's going to be equal compression from one side of the flange to the other. If the top flange is fully under compression, then it's more likely to experience lateral torsional buckling. But if we have M1 getting smaller to a point where potentially M1 is actually 0, then the compression in the middle of the beam here is actually half of what it would be if we had a uniform bending moment. And the compression at the left-hand side in the top flange is going to be 0. And so we have less compression overall in the top flange as M1 gets smaller. And so that makes sense. If the compression overall in the flange reduces, then the bending moment resistance is going to increase. We're less likely to get lateral torsional buckling in those situations. Okay? Does anyone have any questions about what kappa or omega 2 are, or any other questions before we continue on to some typical situations you'll encounter? Okay, so that's great. We got a segment here. What does that mean for us, generally speaking? Well, if we had a girder loaded by a single joist, right? So this is that's the girder, and it's loaded by a joist or a couple of joists, right, at a single spot. We've got a load P that comes into the middle of the girder, and in addition to the load, the joists provide a single point of lateral restraint so that that beam can't buckle in or out of the page as we're looking at it. Well, what does that do for us? There's a couple things. One, it reduces the unbraced segment length, right? So in this case, we're looking at L1 and L2, and as long as the point load is in the middle, L1 is equal to L2 if the load is in the middle. So that presence of the joist there is first, it's going to reduce the unbraced segment length. And so if we reduce the unbraced segment length, we're going to increase our critical elastic bending moment. It also changes the shape of the bending moment diagram compared to what we talked about the other day. And so in this case here, what we're going to do is we're going to break up this beam into the two segments that are unbraced. And so we're going to have a left-hand segment and a right-hand segment. Basically, if we look at the shape of the bending moment diagram, right, so if we look at this segment over here and we look at the bending moment diagram, we have M2, we have 1. M1 is equal to 0 in this case because it's at the start of the beam where we have a pin and a roller and we're not going to develop any significant bending moment. And so in this case, we've got an unbraced segment on the left with a value of L equal to L1 and a segment on the right that's also going to have an unbraced segment length of L2 in this case. So here we have an unbraced segment length of L1. Over here, pretty much the same thing, M2, M1, and L2. So we'd use this value of L. So for example, left-hand side, we'd use a value of L1 to calculate the critical elastic lateral torsional buckling moment. And what value of omega 2 will we use in this case? What should omega 2 be in this situation? Well, we just looked at this, right? So if the moment at the left-hand side is 0, kappa is 0. We can go back to the equation for kappa. We get omega 2 is 1.75 plus 0 plus 0. And so we're going to get omega 2 is equal to 1.75. Okay? So in this situation, omega 2 is equal to 1.75. Over here, omega 2 is equal to 1.75. And so if we were to compare this to the example we did the other day where we had uniform moment M1 at the left, M2 at the right, and the full unbraced length of the beam equal to the length of the girder, basically we're increasing the moment, we're increasing MU by 75% just because the shape of the bending moment diagram is different, which seems perhaps weird at first glance. And we're also going to increase it based on reducing the unbraced segment length to L1 instead of the length of the girder. Okay? So if you encounter a situation where you have a girder with a single point load, basically omega 2 is going to be 1.75, and then you just use half the length of your beam to calculate the value of MU. So far we've seen an equation here that we can use to calculate MU, or omega 2, to increase MU depending on the moment gradient. We've seen from the equation that omega 2 is 1 if M1 is equal to M2, which is good because that makes sense. And it's equal to 1.75 for a situation where we might have a moment diagram that looks something like this. Does anyone have any questions about any of the things we've talked about so far before we continue on through a few different cases? Okay. So that's the case of a single joist. It's more common to have more joists, and so let's say we've got two joists. Here we've got loads coming in from the joists. The X also denote that those joists are providing lateral restraint to the compression flange. And so now we have three segments that we need to consider. Right? So here we've got L1, here we've got L2, and here we've got L3. So we've got three segments to consider the lateral torsional buckling resistance for. And we're going to calculate them based on L1, L2, and L3 for the three segments. And we're also going to use the associated value of omega 2 to calculate the value of MU for that segment. At first glance, this seems like a lot of busy work because, oh, well, now I've got to calculate, MU for this one, and I've got to calculate MU for this segment, and I've got to calculate MU for this segment, and calculate the corresponding value of the moment resistance, right, for the different segments. It's not that complicated because we're actually going to see for situations like this, it's going to be relatively simple to identify which of these three segments is going to be more critical than any of the other segments. Can anyone guess which of these three segments might be more critical before, I don't want to show you yet, but does anyone have a sense for which of these three segments would be more critical in terms of lowest moment resistance for the highest moment demand on that segment? Any takers? Yeah? It's the middle. That's great. Why? Right, so if we look at the shape of the moment diagram, right, the moment is equal on both sides, so the entire top flange is in compression. The other ones have moment of 0 and 0 at the start and end respectively. And so, if we look at the segment overall, this segment has the same factored moment on it, right? There's going to be a moment at the right-hand side equal to whatever M is here. So maybe I'll just write this as M, and M. Right, and so if we're to break out the segment at the left-hand side, we have M2 and M1. This is equal to 0. That's equal to M. The middle segment has a moment of M2, M1, both of which are equal to M. And then the right-hand segment here, we have M2, M1 equal to 0, M1 equal to M. And so we've got three different segments with three different moment gradients. So the shapes of the moment diagrams are different. Let's just assume L1, L2, and L3 are the same so that we can just get rid of that. Why is the middle one more critical, do you think, then? So we've got moment equal to equal moments at both ends of the beam. Why does that make that segment more critical? The unbraced segment length is the same for all three. The maximum moment that we would check, so MF is still the same for all three segments. Why is the middle segment more critical? Well, L is the same for all three. We'll assume it's just equal to, the length of the girder over 3 is the unbraced segment length. But we also have omega 2 values to consider. what's omega 2 for the left-hand segment? We've done this twice now, right? 1.75. What does that do to the value of mu? It makes it bigger. What's omega 2 for the middle segment? We've done this already a couple times. It's 1, right? 1.0. And over here, omega 2 is 1.75 also. Okay, so in terms of calculating mu, this one's going to have an mu value that's 75% bigger than this one, because omega 2 is 75% bigger. And likewise over here, it's going to have a higher value of mu. The middle segment, when we do our moment resistance calculations, you're going to calculate mu. The lowest value of mu is going to be for the middle segment, because omega 2 is the smallest, and L is the same for all three segments. The section doesn't change from one side to the other, so the plastic section resistance does not change. It's the middle segment of this girder that's going to be most critical. Okay? So we don't need to do moment resistance for this segment and this segment and this segment. We already know that when we do our moment resistance calculations, the middle segment would be most critical. Okay? When would that change? Well, it might change if L2 is less than L1 and less than L3, right? If the point loads were closer together here and the lateral restraint was closer together, then we might be saying, okay, well, L1's bigger and omega 2 is bigger, so it's kind of a wash. And we might say, okay, L2 is smaller and omega 2 is smaller, it's a bit of a wash there. And in fact, it's not uncommon, I wouldn't say it's overly common, but it's not uncommon to place the joists even just a little bit closer to the middle of the girder just to make the use of the section a little bit more efficient, because that increases the unbraced moment resistance of the middle segment and makes it more comparable to the two outer segments. Okay, anyway, that's one other situation. Does anyone have any questions about the conclusions I just made here? I just said, based on the evaluation of the three segments, omega 2 for the middle segment is smaller, so the moment resistance will be smaller. That's the only one we really need to check if the lengths are all the same. Does anyone have any questions about that before we continue on to a couple more cases? Okay. What if we've got 3 point loads? I guess I should start here. Let's say we've got 3 joists. Well, if we have 3 joists, then the shape of the bending moment diagram is going to look something like this. And so we can break it up again into our segments. Let's just assume, for all intents and purposes, that L is the same for each segment, L over 4, L over 4, L over 4. Which of these segments do you think are going to be more critical? Well, this is slightly different from what we looked at previously. Over here, we've got a segment with M1 is 0 and M2 is some value. Basically what we've got here is we have a moment, and actually at these other locations we're going to have, if you were to draw the bending moment diagram, these work out to 0.75 times the maximum moment. And so on the left-hand side, we have a segment with 75% of the maximum moment on the section. And in the middle 2 segments, we have a symmetric situation where M2 is equal to M, M1 is equal to 0.75 M. So this is even more clear, at least I would hope that it's more clear, that this is going to be the more critical segment, and it's going to be the more critical segment for 2 reasons. One, the moment on the section is actually higher, right? The maximum moment on the middle segment is bigger than the other ones by about 1/3. And because the moment diagram is closer to being constant, right? We've got a kappa value here of minus 0.75, and that's going to make omega 2 closer to 1. It's not going to be equal to 1 because the moment diagram is slightly different, but it's going to be equal to a little bit more than 1. And so if we were to, let me see, I might have that slightly wrong. Let's call this 0.67, and let's just change all these to 0.67. I think I did my mental math there slightly wrong. in any case, we end up with kappa is minus 0.67. And if we were to plug that into the equation for omega 2 is 1.75 minus 1.05 times 0.67 plus 0.3 times 0.67 squared. And we get an omega 2 value in this case of about 1.18. Okay, so omega 2 is still a little bit bigger than 1 in this case because it's approaching a constant moment diagram, but it's not equal to the 1.75 that we'd get for the first segment. And so again, for this girder, the moment's bigger in the middle segment, omega 2 is smaller, so the moment resistance is going to be smaller. Moment resistance is lower, factored moment is higher. You should see the pattern here. When you're looking at your girders, the middle segment is going to be the most critical. Okay? How is this moment diagram going to change if we go from 3 to 5 point loads to 7 point loads to 9 point loads? What's going to change about the middle segment if we increase the number of point loads and we look at odd cases? Here we've got 3 point loads, and so we've got a moment diagram that's almost constant but not quite. As we increase the number of point loads and keep them as odd, so if we had 5 point loads instead, then M1 is going to get closer to M, kappa is going to get closer to minus 1, and omega 2 is going to get closer to 1. Okay, so if we have an odd number of joists loading the girder, we're going to approach omega 2 is equal to 1. What do you think is going to happen if we were to increase the number of joists we have loading our girder and we have an even number of joists? How is the middle segment going to change as we add more joists? Well, let's say we had 4 point loads. Let me go back here. Let's just say we, where should I draw this? Maybe I'll draw it here. So let's say we go to 4 point loads. So 1, 2, 3, 4. Well, the moment diagram is going to look something like this. If we have an even number of joists loading this girder, is the moment diagram in the middle segment ever going to be not constant? No. When you have an even number of joists loading your girder, you're always going to get a constant moment diagram in the middle segment. And so it doesn't matter how many joists you have loading, as long as you have an even number of joists, and they're symmetrically loading the girder, of course, then omega 2 is going to be 1. Okay? So for those of you, I don't know how many of you have an even number of joists loading the girders on your design projects, but if you have an even number of joists loading your girder, you can be safe using a value of omega 2 is equal to 1. Of course, as you add more joists, L is going to get shorter, right? And so you're going to increase the moment just by increasing or reducing the unbraced segment length, but you're not going to be able to take advantage of any increase due to the moment gradient for the middle segment of your girder. For an odd number of joists, you're going to get closer and closer and closer and closer to constant. And so if instead we had, let's just say, I don't know, let's just add a bunch like this. If we had instead 7 point loads, our moment diagram is going to look something like this. Drawn very crudely, of course. I don't even know if that's the right number of segments, but anyway, what I'm trying to get at here is that this moment diagram is going to get closer and closer to kappa is equal to minus 1. And so as we add more joists, kappa is going to approach minus 1, which means omega 2 is going to get closer and closer to 1. What I'm trying to communicate here is that for the design of girders in simple frame buildings, it's conservative and not unduly conservative to take omega 2 is equal to 1. Okay, because even in this case where we have 3 point loads, omega 2 is equal to 1.18, that doesn't do too much for us. And as we add more joists, omega 2 is going to get smaller and smaller and smaller. Now, the only case that that's not true is if you have one joist, because if you have one joist, that's an odd number, but we do get a significant increase in our omega-2 value. So in this case, if you have a single joist loading your girder, you probably want to take advantage of omega-2 to increase MU, but the more and more point loads you add, the less advantage you actually get, because the moment gradient gets closer and closer to constant as we add more joists in the critical central region of the girder. Okay. So we've talked about omega-2, how we'd calculate it, how we might get different values of omega-2 for different unbraced segments of our girder. If we look at unbraced segments of our girder, omega-2 gets closer to 1 as we go towards the middle. The moment on the girder gets higher and higher as we go to the middle. And so we've identified that for girders loaded by joists, the central segments are going to be more critical. And it doesn't matter if you have an odd or even number, the middle segments are going to be more critical than the outer segments. Does anyone have any questions about any of that stuff before we go on to a different situation? Okay. So far we've talked about situations where when we have a point load from a joist on a girder, we also have lateral restraint. It's not always the case that a load on a beam is going to provide lateral restraint. And the example I often use, I don't know if has anyone been in like a paper mill or anything before, or has anyone been in a mechanic shop before and like lifted a motor with a chain block on a beam, anything like that? Well, just imagine that you've done that before. You're trying to lift something heavy, you've got a beam suspended from the ceiling, and you've got this little trolley, and basically you're trying to lift off the center of this beam, or at 25% of the length of this beam, you're trying to pull up some kind of heavy load down here, and basically it's just hanging from a chain, okay, or hanging from a rope. And basically from this side to this side, the compression flange isn't braced anywhere along the length, and you're just loading it because you've got a heavy load that you're trying to lift up from the ground. Do you think that a heavy block hanging by a rope provides lateral restraint to that beam against lateral torsional buckling? The right answer is no. You can't. I guess you're just literally hanging from a rope. You can't prevent it from resulting in lateral torsional buckling. And so it's quite common for the design of monorails, for example. Monorail is a little beam that has a trolley that basically has a hook on it and carries heavy things from one side to the other. There's a point load pardon me, that can change location, but it does not provide any lateral restraint to the compression flange. So in this case, if we were to look at the bending moment diagram, right, we get something like this. And if we think of the unbraced segment, well, the entire beam is unbraced, and so we have M1 is equal to 0, M2 is equal to 0. And you think, well, what the hell do I do with that? That doesn't sound right. I have a moment gradient that's not constant over that beam, but if I use the equation that I got before, basically I have 0 and 0, so I might say, well, kappa 0, or kappa 0, I guess. I cannot use kappa 0 or kappa is 1. In this case, I get 1.75 or 1, and that just doesn't make any sense. We've got a moment diagram that's no longer linear, right? So it's linear technically, but it's piecewise linear. And so from here to here, and from here to here, along the unbraced segment, which is now the entire length of the beam in this case, it's not a linear function from one end to the other. It's piecewise linear, and it's not a constant linear function. And so the equation for omega-2 that we talked about before doesn't work for us anymore in this particular case. So if my iPad will proceed, there we go. Some really smart people from the University of Alberta had recognized that for the design of certain systems like monorails, where the lateral restraint doesn't correspond with the point load that's loaded by the joist, we need a different value of omega-2 because we still can take advantage of the fact that the moment diagram is not uniform. And basically what they came up with was an equation for omega-2 that looks something like this: 4 times the maximum moment in the segment divided by moment of the maximum segment squared, plus 4, 7, and 4 times MA, B, and C squared, respectively. And basically what these are, this one's pretty straightforward. It's the maximum moment. You see it in the numerator and the denominator. And then MA, B, and C are the quarter point moments from the moment diagram. Okay, so if we were to come back and look at the situation, and draw the moment diagram somewhere up here. Basically, this is the maximum moment. And then we go to the quarter points. And so here, here, and here. And so in this case, we also have MA, which is equal to M max. We have MB, which is equal to 0.67 times M max. And we have MC, which is 1/3 of M max, or 0.33. Okay, so we have to base our equation for omega 2 now based on the maximum moment as well as the quarter point moments. In this case, M max and MA are coincidental. And the other thing that's not important here, it does not matter what the value of M max is. It's just a function of the shape of the bending moment diagram. And so for all intents and purposes, I'm just going to say, okay, let's just say M max is equal to 1. In this case, we have, maybe I'll just write the equation for omega 2 here. We get omega 2 is equal to, come on, iPad, 4M max. So we get 4M max divided by the square root of, oops, come on, iPad, M max squared plus 4MA squared plus 7MB squared plus 4MC squared. And that's 4 times 1.0 divided by the square root of 1.0 squared plus 4 times 1.0 squared plus 7 times 0.67 squared plus 4 times 0.33 squared. And if we do this math, we end up getting an omega 2 value of about, am I doing that right one? There we go. Yeah, 1.37. Okay, so in a situation like this, based on where the load is, the moment diagram has a certain shape. Based on the shape of the moment diagram, we take the maximum and the quarter point moments, apply this more complicated equation for omega 2, and that gives us 1.37. Okay, so this is something that makes sense. It's not going to be 1.75 because the shape just doesn't make sense for 1.75. It's not going to be 1 because it's not a constant diagram. This equation gives us an omega 2 value of 1.37, which means we can increase our critical elastic buckling moment by about 37%. If we were to do the same thing here, well, in this case, we just have slightly different quarter point moments. In this case, we have M max, and MB is also equal to M max. Then we have MC is a half, M max, MA is equal to a half M max. And just in the interest of time, if you do the calculations based on those values of MA, MB, MC, and M max, we get an omega 2 value of 1.26. So this is a little bit of dialogue that might not be necessary, but if we have a point load P that kind of moves along the length of the beam, it's some kind of crane carrying beam, the point load moves along, where is the point load going to be when the moment is maximum? Or what position of that point load will cause the maximum moment on that beam? Well, I hope that everyone remembers that if we put the point load in the middle, that generates the maximum moment, right? And as we move from left to right, based on this example, if the point load's closer to the left-hand side, we had omega 2 of 1.37. As that point load moves towards the middle, the moment diagram shape changes and we get a value of 1.26. As we shift the point load from left to right, the moment increases as it approaches the middle. Omega 2 gets smaller as we approach the middle. And so if you wanted to calculate the strength of this beam, you would put the point load in the middle, get the maximum moment, and use this omega 2 value to calculate the moment resistance. Okay, so for beams like this, the most critical situation is when we have a point load in the middle of the beam, because omega 2 is going to be smallest and the actual moment on the beam is going to be largest. Does anyone have any questions about that before we talk about the last couple things? Okay. So I showed you a plot before for what the moment looks like. And so if we're calculating the moment resistance, we have MP in elastic lateral torsional buckling for that second equation, and then MU, which is the elastic lateral torsional buckling equation. So it's easy for us to see how L changes the moment resistance. But now I've just added another plot here to show how omega 2 changes the moment resistance. Okay, so for really, really long beams, where the elastic lateral torsional buckling strength is going to govern the resistance, omega 2 directly increases the bending moment resistance. As we approach the inelastic lateral torsional buckling range, omega 2 still increases the moment resistance a little bit, but we're not getting the full 35% or 75% in those two cases for those values of omega 2. And for really short beams, of course, we can't exceed the plastic moment resistance. What changing the bending moment diagram does help is it helps to increase the length that you can have unbraced before you get to the plastic moment resistance. And so in this case, if omega 2 is 1, an unbraced segment length of about 3 meters or slightly more will result in having lateral torsional buckling. But as the bending moment diagram shape changes up to omega 2 is 1.75, then we don't have to worry about lateral torsional buckling until almost a 5 meter unbraced segment length. Okay, so omega 2 increases the length that you can have unbraced before lateral torsional buckling becomes an issue. And as lateral torsional buckling becomes an issue, it helps you increase the respective strength against lateral torsional buckling. Okay, any questions about that concept before we do a very quick example for how omega 2 might change the strength of the beam we looked at the other day? Okay, so let's do this real quick. We basically did the same problem the other day, right? Pin roller. We looked at this beam. It was a W610 by 153. Last day we had a moment at the left and a moment at the right. They were equal. We had basically a constant moment diagram, and we calculated the moment resistance of that beam. Now we're going to say, okay, let's assume that the moment comes from a point load at the middle of the beam that also provides lateral restraint because it might be a joist. How does this loading scenario change the calculated moment resistance for this particular beam? Does anyone have any questions about what we're trying to do in this example before we get into the calculations? Okay. So we already know that this is class 1, right? That doesn't change, right? So it's a class 1 beam, and we know that MP from the other day was equal to 1,587. Okay, so the first step would be get the section class and then calculate MP or MY. In our case here, we already know it's class 1 from last day, and that MP is 1,587. What we need to do now is see what value, pardon me, Jesus, what value of MU we're going to be using, or what value of L. The other day we used the full length, 7.5 meters, but now the presence of this joist is reducing the unbraced length of our segments, and so instead we have 3.75 meter segments. Right, so L is going to be half what it was the other day. L is 3.75 meters. I don't know why I made an M with 3 humps. And our moment diagram is going to be a little bit different. Right, so our moment diagram for this situation is going to look like this. Does it matter which segment we're looking at here? Is either one of these segments going to be more critical than the other one? No, they're the same segment, basically. It's symmetric. What value of omega 2 would we use when looking at either of those two segments? We've done this 3 times now. 1.75. Okay? So the plastic moment resistance of the section doesn't change, but the calculation of MU changes. Okay, so MU is omega 2 pi over L times the square root of E IY GJ plus pi E over L squared IY CW. Okay, so the only thing that's changed here now is that omega 2 is 1.75. L is 3,750. L also shows up in here, right? We've got some stuff plus pi E over 3,750 squared IYCW. To make sure we get out of here in a reasonable amount of time, all I'm going to do here is write out what the resulting critical elastic moment is. In this case, we get 2,449 kilonewton meters. Okay. Does anyone remember what it was for the example the other day? Was it smaller or bigger than this? You don't even have to know what the answer was. Is mu going to be bigger in this case than it was the other day? Yes. The other day was 821 because L was much bigger. Omega 2 was 1. And so this is compared to 821 kilonewton meters that we got the other day. Okay? So 3 times stronger against lateral torsional buckling than the beam we had the other day. So if we were to calculate the moment resistance, we compare mu versus 0.67 MP. Right? So mu is 2,449. 0.67 MP is equal to 1,063 kilonewton meters. Is mu, well, I'm just going to say it. Now mu is bigger than 0.67 MP. Yesterday it was smaller. And so basically this is going to change how we calculate the moment resistance. Okay, because mu is greater than 0.67 MP, MR is 1.15 phi MP times 1 minus 0.28 MP over mu. That can't exceed phi MP. So we get 1.15 times 0.9 times 1,587 times 1 minus 0.28 times 1587 divided by 2,449. That equals 1,345 kilonewton meters. And we have to check that that's less than or equal to phi MP. 0.9 times 1587 is 1,428 kilonewtons. Okay, so reducing the segment length and increasing omega 2 gave us an mu value that was 3 times higher than it was the other day. That results in a different calculation of the moment resistance because we're in the inelastic lateral torsional buckling or the plastic moment resistance range. We use this equation, we get a moment resistance of 1,345, which is less than phi MP, which tells us that's just into the inelastic lateral torsional buckling range. Okay? Does anyone have any questions about that example before we move to wrap things up? Okay, well, now you should be able to do the things that we talked about, identify critical unbraced segments in a steel girder, and calculate the moment gradient factor for any of these unbraced segments. Does anyone have any questions before we run off to next class or hang around before we wrap up the lecture for the morning? All right, thank you for humoring me for the last 5 minutes or so. We'll see everybody on Friday morning.